Welcome back to Quantum Mechanics for the Working Professional. This is a course meant to take folks with a mild technical background through the rudiments of quantum mechanics and quantum computing. I'm Sean, I'm your guide through this material. In this third section, we're going to learn some new mathematical tools to help us model particles in 3 dimensions. In particular, we'll learn about the complex numbers, operators that represent the spin of a particle in 3 dimensions, and we'll specifically learn those in terms of the famous Pauli matrices. Finally, we'll learn how to take the commutator of 2 operators and package that whole thing together in the context of what mathematicians would call an algebra. As always, we'll have a write-up to accompany this lecture posted online, and we'll drop the link in the show notes. Inside, you'll find links to additional reading, as well as references, and of course, exercises, which I strongly recommend that you partake in, or at least attempt, to assess how well you've understood this material. If you haven't registered for the course yet, I strongly encourage you to. It's free, but if you need some kind of extra accountability mechanism to help push you through that material, we can offer that for you, as well as keeping you up to date with any bonus material, hints, tips, and of course, future lectures. Great, let's get started. All right, we've been at this game, well, it's bright. All right, we've been at this game now for a few episodes. Starting today, we're going to ramp up our mathematical sophistication. And the first step along that path is the complex numbers. A common complaint about the complex numbers is that they're not real. And part of that might be unfortunate terminology, right? Because any complex number, as we'll see, has a real and imaginary part. And the word imaginary is really unfortunate because complex numbers do have a real physical significance that can be measured in experiments. But first things first. Let's recall from elementary algebra that not all equations that I can write down have solutions. As you may recall, x squared plus 1 equals 0 is impossible to solve. In our familiar system of numbers, there's no number whose square is negative. As they do, mathematicians have worked their way out of this problem by simply defining the quantity I as equal to the square root of minus 1, so that I squared equals minus 1. And the solution to the equation above can be written as x equals I. As if acknowledging the cheat in the definition of I, mathematicians call any number that solves such impossible equations, that is, any number proportional to I, an imaginary number. Imaginary numbers prove to be incredibly powerful tools. The complex numbers are all linear combinations of real and imaginary numbers. A complex number z is typically written as a plus ib, where a and b are ordinary or real numbers. We can then refer to the real and imaginary parts of z as a and ib, respectively. Often, we will represent a complex number by a 2-dimensional real vector. So you can think of that either as a column vector with a and b in the 2 components, or a row vector, a and b. Alternatively, we can represent this ordered pair, a and b, as a point on the so-called complex plane. There are 2 concepts in the study of complex numbers that are useful to know. The first is the complex conjugate. The complex conjugate of z, known as z bar, is a minus ib. It's a simple map where I goes to minus I, which can be thought of as reflection in the plane that sends the vertical axis to minus itself. The complex conjugate brings us to our second important concept in complex numbers. Consider z times z bar. Expanding that product out shows that it's equal to a squared plus b squared. Put differently, the modulus or magnitude squared of a complex number z is simply z times its complex conjugate, z bar. This is exactly the same as the modulus of a two-dimensional real vector space. Incidentally, the modulus is useful in defining yet another representation of the complex numbers, that one using polar coordinates. Here r is the modulus of z, and the angle in the plane, the arctangent of b over a, is called the phase. Engineers will sometimes call this the phasor representation. Going forward, we will use complex numbers with reckless abandon. In particular, we're going to use them in the definitions of our quantum state vectors, so let's see how that goes. Recall that a generic quantum state for our two-level system, a ket vector psi, has two components with two scalar coefficients, alpha up plus beta down. Starting today, we will promote alpha and beta to complex numbers, which means that there are actually 4 real numbers used to represent a generic quantum state psi. The main thing to note here about the change to complex numbers is that now the dual or bra vector psi now uses complex conjugates for its coefficients. In row vector form, we see that alpha bar and beta bar are now the two components. We do this because now the inner product of psi with itself is real and strictly positive, as it is the sum of the squared magnitudes of alpha and beta. Thus, the magnitude squared of a generic state vector is actually the squared sum of 4 real numbers, 2 each of the components of 2 complex numbers. It's important to observe that in general, an inner product between bras and kets, such as the upstate with psi, is a complex number, in this case alpha. This means that there is now a distinction between up with psi and psi with up. They are complex conjugates of one another. Of course, the probability, the physically measurable thing, depends on the modulus squared of these inner products, so will always be a positive real number. That formula for the probability of finding psi in the up direction reminds us that we are invoking the normalization convention for psi. As we've learned, not all of the 4 real numbers that comprise the state vector psi are physically meaningful. We always have to normalize the probability distribution between 0 and 1. By convention, we have set the magnitude of psi to 1, so that the mod square of those 4 numbers is constrained to equal 1. This fact has an important geometric interpretation. Such an equation defines the unit sphere in 4 dimensions. That is, the unit 3 sphere, a 3-dimensional sphere, compared to the familiar 2-dimensional one that we deal with in day-to-day life. If that's really esoteric for you, don't worry too much. It's very similar in form to the familiar equation that defines the familiar 2-dimensional sphere in 3 dimensions. X squared plus y squared plus z squared is equal to 1. The relationship between spin and the quantum state is a very subtle one. So if you find it confusing, do not be alarmed. It is confusing. To fully understand the relationship between spin and the quantum state, we need to familiarize ourselves with 2 facts. First is that there are actually 3 real numbers that parameterize a 2-level system, a spin 1/2 state, like a silver atom or an electron. And the second is that measuring a quantum system actually changes its state. So let me explain. The 3-dimensional sphere in 4-dimensional space can be parameterized by 3 separate angles, 3 real numbers. And these 3 real numbers will actually correspond to the 3 directions in which we can measure spin. In other words, the 3 sphere parameterizes our quantum state in terms of spin in the x, y, and z directions. By now, hopefully you're familiar with the spin operators Sx and Sz, which are used to measure a particle's spin in the x and z directions, respectively. These are represented by 2x2 matrices that we've studied extensively in the exercises. Now that we're more mathematically sophisticated, we can introduce the final such matrix Sy, which has imaginary numbers for its entries. Together, these 3 spin operators form a 3-dimensional vector in 3-dimensional space, a regular, old-fashioned XYZ vector that hopefully you're very familiar with. So the vector of 3 spin operators is related to the fact that we can orient the magnet of the Stern-Gerlach device in any direction that we choose. notice that it's a vector of matrices, a vector of operators. So there's two things going on here that I want to draw your attention to. On the one hand, we have a spin operator vector in three-dimensional space. And on the other hand, we have a quantum state vector psi, the ket, which is a two-complex dimensional vector in the abstract two-dimensional state of quantum states. So this means that the action of the vector of operators S on the state vector psi is both a three-dimensional vector in space and a two-complex dimensional vector in the space of quantum states. You might want to watch this part over and over again until this fact sinks in. And it's okay if it takes a while. It always does when you're learning this stuff. 90% of the reason why we use vector notation is because it makes actually physically writing the equations out much less cumbersome. Now, as you've seen in the exercises, Sx and Sz come with their own basis of orthogonal normalized states, up and down, for each of the x and z directions, so that if we measure the quantum state in the x direction and it's up, it would be in the state up x. The spin y matrix has its own sort of orthogonal states too, representing the spin up or down in the y direction. These are simply given by 1 over the square root of 2 times 1 and I for spin up, and 1 and minus I for spin down. As an exercise, you can check that they're orthogonal and that they're normalized and so on and so on. By the way, since they have imaginary numbers for components, you need to be careful about dealing with their associated dual or bra vectors, because we take the complex conjugate. Coming to terms with the full three-dimensional vectorial nature of the spin operator and the concept of spin brings us a whole new concept of orthogonality. Right? Because the directions x, y, and z are orthogonal in like a geometric sense. But the quantum state itself, the information contained within the quantum state, is also orthogonal in the sense that if you measure a two-level system like a qubit, like a silver atom, in the x direction, if you measure its spin in the x direction, it loses all information about what it should be doing in the y or z direction. We've already kind of explored this idea in the exercises. If we know that the physical state is in a definite spin state, like in the x direction, like what happens after we measure it with a Stern-Gerlach device, then the variance is 0. We have 100% confidence what direction the state is in. Whereas if the expectation value is ambiguous, for example, if it's 0 for a two-level system, then the variance is in some sense maximal, hbar squared over 4, because we have no idea what's going to happen when we measure that state in that particular direction, say the z direction. Did you catch that? There's a subtle point there that's worth repeating, and that is that in quantum mechanics, we only care about what happens when you measure something. We don't care about anything else. That's the only physical fact that concerns us. And a fun intellectual exercise is to go back and compare that perspective, that subtle change in perspective, from every other physical concept you've ever been taught. There's one point that I wanted to make about these spin operators, these so-called Pauli matrices, and we hinted at it a little bit in the exercises, but what happens when we measure spin in, say, the x direction and the z direction in rapid succession? Mathematically, this just amounts to multiplying matrices. So let's do that. Computing, we find something sort of familiar. Do you see it? Here, let me multiply through by I and minus I. The product of spin in the x and z directions is nothing more than the spin operator in the y direction. Well, a little bit more. There's a constant out in front. We've already learned that we can't measure both spin in the x and z directions at the same time. That information doesn't exist. But yeah, what happens when we measure them in rapid succession? What happens is we effectively measure spin in the y direction. This kind of mathematical structure you might have seen before when dealing with vectors in 3 dimensions. It's similar to something called the cross product, and it is often rather laborious to work out in general. To make this analogy more precise, we're going to introduce the concept of a matrix commutator. The commutator of two matrices A and B is simply defined to be AB minus BA. It's a measure of how much the two matrices A and B fail to commute. We'll see this a lot in quantum mechanics. To practice, let's take the commutator of the spin operators Sx and Sy. Well, what do we get? Let's work it out. Sx times Sy is nothing more than I h bar over 2 times Sz. And Sy times Sx is almost the same thing. There's just a minus sign. So when we take them together, the commutator of Sx and Sy is nothing more than I times h bar times Sz. In other words, the spin operators in the x and y directions fail to commute. And how much do they fail to commute by? I h bar Sz. In classical physics, something you may have learned in high school, you can measure anything that you want. In particular, you can measure the spin of a baseball in the x, y, and z directions at the same time. You could do it with a video camera. Spin angular momentum, after all, is just a number. But what the commutator shows us is that you cannot measure two components of the spin operator at the same time. There's an obstruction. Remember, that information just doesn't exist. It's not defined. If you measure them in order, Sx then Sy, you will get a different answer if you measure them in the different order, say Sy and Sx. A complete set of these relations involves all possible commutators of all spin operators, Sx, Sy, and Sz. And just like the cross product involves a bit of vector algebra, physicists working with these operators in this way call this the algebra of angular momentum. Spin angular momentum. For completeness, recall that the square of any of the spin operators is itself proportional to the identity matrix, that is h bar squared over 4 times 1. Incidentally, this calls our attention to the importance of that constant, h bar. It encodes a level of error or uncertainty that quantum mechanics introduces. You'll see these factors, I, h bar, virtually all the time when working with commutators. Well, that's the end of section 3. Next time, we'll discuss a very specific kind of operator on the space of quantum states, notably the energy or Hamiltonian operator. Until then.